Again, welcome to this program. This is one in our occasional series of Bay Area computer history perspectives. I'm Peter Nurksey from Sun, and also organizing the program is Jeannie Treichel, also from Sun. Perhaps Jeannie could stand up a moment, yeah, or wave. Yeah, right. So Jeannie and I appreciate any and all suggestions for future programs. The next program in the series will be October 24th, Niels Nielsen at SRI talking about Shaky, the major contribution from the Bay Area to robotic history. So our past programs have often been in the form of panel presentations, like history of Ethernet, for example. But on the subject tonight, Dynabook, it's pretty clear there's really one person to talk about it, and that's Alan Kay. And Alan has agreed to talk to us tonight. Thank you very much, Alan.
Well, one of the things, there are enough people with gray hair in the audience so that I can't lie as much as I usually do when I tell this story. The other thing is, a couple of years ago, I wrote a fairly extensive history of Smalltalk, which is published as a preprint in the SIG plan as part of the Hopel 2 proceedings. It's going to be in a book sometimes. We have some in our office. I'm going to leave one with Peter and Jeannie. And it's more detailed, well, it's much more about Smalltalk than the Dynabook. It has that story in there. It's more detailed than I can cover tonight. One of the things I discovered when I wrote this is that it's simply not possible to tell the truth when you're doing a history. Even though there are about 50,000 words in it, I had to leave out, I apologize in the beginning for how many things I left out. I also found myself leaving out an enormous number of really juicy and very funny stories, just because the page limit was getting longer and longer and longer. And it was impossible to express, even in this longer thing, all the different intellectual debts and so forth. And again, tonight, the story that I tell you can't possibly be the truth. And a lot is going to be omitted. And however, some people in the audience might help my recollection on a couple of cases that, in case I'm showing early signs of Alzheimer's on this. Although it turns out that Alzheimer's is okay for one of these things because you tend to remember the stuff that happened earlier quite in detail. So I think I do remember that. Now, what I'm going to do is, I was originally asked to recapitulate the talk I gave at Hopel, but that was really intended to be supplemented by the paper, which many of you have not read. So I've done a different talk, and I'm going to move through it as quickly as I possibly can. If I don't digress too much, we might get done more or less on time. If I do digress, then time will run out before I ever get to the invention of the Dynabook. We'll see. So let's see. I'm going to, I have a flat screen display here, which is for controlling the video, but I don't see how to control the slides.
Okay, slides. There's video, audio, and his slides.
Oh, all right. Well, I have to go to another page. Okay. This is a modeful user interface. Okay, slide projector on. First one.
You just need to go forward here.
Okay, it says fast forward though.
Yeah.
I don't want to go, okay. So the context for this, the other thing I found out in preparing this talk is a lot of my best explanations came post facto. This is partly because we found it extremely difficult to explain these ideas to Xerox. And over the years, I found better examples. However, in order to keep this historical, I want to try and stick pretty much with what we were thinking at the time. And so I've left out some of the better ways of explaining this stuff, but I think there's enough context now This is after all, let's see, 27 or 28 years later. There's enough context, so it shouldn't matter. But I want to set up one piece of context, which in fact we did think about back then, although we didn't completely realize that we were doing it ourselves. It was much more when we were thinking about how to help kids be creative, and that is an idea from Arthur Koestler's Active Creation, which was written in the mid-60s. And one of his models of the creative act is that we tend to think in context. And the context here is pink, and here's a train of thoughts working in its way through the pink. You can think of the pink as a paradigm, think of it as a goldfish bowl, you can think of it as a box, whatever you like. But the idea is that there seem to be constraints in the human mind to keep you thinking about one reality at a time. And so when you have little deviant thoughts, little blue thoughts, they get shoved down immediately, and you go back to pink thinking. But every once in a while, maybe when you're in a hot tub taking a shower, out jogging or something, one of these blue thoughts breaks through, and all of a sudden you see that this pink thing that you were thinking about is really a blue thing, and moreover, it's much more interesting as a blue thing than it was as a pink thing. So this is what Koestler calls bisociation, the colliding of two contexts, usually by analogy or metaphor. And of course, 90% of them are really bad ideas. Most ideas are bad. But if you can filter these, this is the way that a lot of creative acts get done. And Koestler pointed out that there are three basic emotional reactions to doing this. If you're telling a joke, it's ha, ha, ha. If you're doing science, it's a ha. And if it's art, it's ah. Because as he points out, a joke is leading somebody down a garden path and then realizing it was about something else all along. And science has this same thing. We often feel that the ideas are all around us. We just can't see them because they're transparent to the context that we're in. And of course, art is, again, being able to see one thing as something else in a more powerful way. So the context for this is that I think in most of these talks, you'll hear people talking about things that they've done. They'll fall into these patterns. You know, we are looking at it this way, and all of a sudden we see it something else, and that gives us a new insight, a new energy. And of course, one of the things, not that this group needs this, but it's amazing how much being generally well educated helps. Because if you're only thinking about pink, if you only have pink things in your brain, it is really hard to get blue ideas. One of the problems with Silicon Valley engineers is that they're too good at what they do, and so they spend all of their time optimizing in the only context that they've learned. So you see, super optimization is not particularly a creative act by Koestler's model. So thinking about other things, and we traverse some of the most unusual things. Dave Smith, who's sitting here in front, found himself, I think to his great surprise, reading books by Ernst Gombrich, one called Art and Illusion, which is about theories of artistic perception, doing a computer science thesis at Stanford. And that wasn't the most unusual book that he read. So the genesis of all this stuff is Memex. This is a picture from the Life magazine version of this article written by Vannevar Bush 50 years ago. There's, by the way, for those of you who are interested, on October 12th and 13th at MIT, there's a 50-year celebration for Bush, and a lot of people who are interested in Memex and linking of information. Engelbart will be there and so forth. They're showing up to commemorate Bush's vision. And as you see in this drawing, the idea was, he said, not too far in the future, people will have in their homes a desk that has inside of it about 5,000 to 10,000 volumes worth of books held on optical storage, that there will be screens for viewing it, there will be ways for putting in information and drawing in information, ways for searching it, and most importantly, there'll be ways for linking the information using what he called paths. And he said there'll be a profession called pathfinders, and pathfinders will make interesting connections between knowledge and cellulose. And you can add them to your Memex as you go along. Now, I was 5 years old in 1945, so I missed this particular article, although I did read Life magazine back then. But Engelbart was in the Navy in the Pacific and did see this. He was in Guam or something. And it started a train of thought that for him gradually culminated in setting up a project to actually do this. And I'll return to that in a minute. I found out about it when I was about 14 or 15 because Robert Heinlein liked to use generic names. So he would take something that's capitalized like Memex and he would uncapitalize it and use it as a generic term used in the future as a descriptive term. So he would say something like, so-and-so used his Memex to do blah, blah. And Heinlein was very reliable about this, and so I discovered early on if I actually looked up these uses of these things, there would be something in, somebody had done something that gave him this idea. So he would give brand names to things, and if you look up the brand names that Heinlein used, you would discover somebody had invented a precursor technology that Heinlein had. So that's how I found out. Science fiction is very useful, especially back in the old days when they actually wrote about science. So fast forward to around 1962, here's Ivan Sutherland sitting at the console of a computer TX2 the size of this room. And I think this is the forum, I believe, isn't it, Jeannie, that Ivan gave his talk? So I'm not going to say too much about Sketchpad. I didn't know about Sketchpad at the time, although I'd started programming for the Air Force a year earlier. And I'm going to show you, what you see on the screen there is Ivan has drawn a bridge in. And Sketchpad was peculiar, even by today's standards, in that you could attach meaning to every element of a drawing, and Sketchpad would attempt to synthesize all of the meanings of the parts into one grand simulation. And the simulation was dynamic if it was under constraint. So if you drew a linkage in with Sketchpad and the linkage was not completely constrained to be still, the constraint solver in Sketchpad would actually iterate its way around through the degrees of freedom, not unlike the way a Prolog program will give you all of the answers for a particular retrieval. But one of the really interesting elements of Sketchpad, and we may not talk about it too much further, depending if I run out of time or not, is that Sketchpad had another peculiar notion, which is that you didn't have to be exactly right in order to be interesting. So the constraint solvers in this were not symbolic constraint solvers. They weren't performing logical operations, but they're actually performing various kinds of arithmetic operations and fit operations. So here's an example of the, let's see, go ahead, go over here, hit play and see what happens. Okay, I'm worried now. So somebody, well, I hope it should be warm. Of course, this thing is playing away, and it isn't showing me the. Yeah. Okay. So let me just back it up a little bit. Yeah. Isn't technology wonderful? Now it's blanking on me. I'm trying to rewind a little bit. Yeah. Oh. Another mode. Okay. So this is a marvelous movie to watch. I'm just going to show you one small part. Yes. Yeah, I don't know what it's doing, really. Okay, he's drawing a rivet here. And one of the things he can do is point. He just told the constraint solver to go on and to line things up in the center of the circle. Oh, boy. Now he's going to distort the thing. And when he turns on the solver again, the solver will line it up so it's symmetric. The center of the arch is the center of the cross piece. So the idea of Sketchpad is you put in generally what the thing is, give it some additional rules that characterize the particular drawing you're trying to make. Those rules can either have to do with the form of the thing, but also can have to do with the meaning of the thing. And here's another interesting thing about Sketchpad. This is, by the way, before there were real computer displays. So every dot is being put up here by brute force by the TX2. But the nice thing about those old calligraphic displays is you got even real-time scale changes, which is still hard to come by on current-day machines. So that's too bad. And now you can get a few more rivets here. And now what's fun is he goes to the master drawing. He says, oh, I better get rid of those cross pieces, so I'll make them transparent. And lo and behold, when we go to the drawing, all rivets have felt that. So this is actually the first object-oriented software system in really strong glory. And anything that you make out of it is in turn a master drawing. So he's made the rivet in the flange a master. And now he's making instances from those. Okay, so I think I'll put it out of its misery here. Okay, we can change to the next tape. So Sketchpad had three really amazing. Boy, that is. There's Ivan. Three amazing, this is what people looked like back then. So I once said to Ivan, in 1 year, almost entirely by yourself, you created the first real interactive graphics program, first system with a window, if you're noticing. It has a clipping window and the drawings on a much larger screen. The first object-oriented software system and the first real-time problem-solving system. You could even call it an AI system. I said, how did you do this? And he said, well, I didn't know it was hard. He actually, in his thesis here, is quite apologetic. If anybody, how many people here read this? What's amazing about reading this thing, besides how great it is still today, is how apologetic he is that it doesn't do more. This is why it's not good to peer too closely into the future. You might get discouraged. Okay, another thing that was happening right at the same time is my vote for the first personal computer, which is the LINC, done by Wes Clark and Charlie Molnar here. One of the design criteria is that it shouldn't loom over you. So it's designed to be small, and actually the first 20 people built their own. They came, spent a summer at Lincoln Labs, and the summer was actually learning about digital electronics, and the project they did was to build their own computer, which they took back with them to their labs. Somewhere between 1,000 and 2,000 of these machines were built in the 60s, mostly for biomedical technicians. These machines also influenced DEC tremendously. For instance, the tape drive that Wes invented for this machine, if you look there, looks like a DEC tape. But in fact, DEC tape was originally called the LINC tape. DEC tapes just held files. They were boring. But LINC tapes actually held pages of the paging virtual memory, this first personal computer had. It only had 2K of 12-bit words on it, but a paging virtual memory on this tape, and it was amazing what you could do with this machine. It was a beautiful machine designed to be taken care of by people in labs for themselves. Had a very nice programming system in it, a beautiful little editor. The debugger on it was quite remarkable in that you, instead of single-stepping your program, you single-step the machine. So the software and the hardware were such that you could actually slow the entire machine down as you move through to see what was actually going on. Beautiful machine. So the other thing that happened around 1962 was Advanced Research Projects Agency phased out of the space business and had some money left over, and for various reasons, all of them justified, they liked this guy, Jack Licklider, known as Lick, and decided to give him a bunch of money to do whatever he wanted. Now, he was a psychologist and had been involved in some of the human factors design of the SAGE system in the 50s. He was both at BB&N and at MIT, and he decided that the destiny of personal computing was to be a complementary partner for human beings. Complementary in the sense that not trying to do what a human does, but to do things that humans don't do well in a very interactive way. So he was one of the people who could extrapolate from pointing light guns at digitally produced radar screens to the idea that this thing might actually help people think. And his phrase up there is in one of his earliest papers in 1960, which is called Man-Computer Symbiosis, was to think as no human being has ever thought, I guess. He was a great guy, and he came up with, he just died a few years ago. Nicholas Negroponte and I are trying to raise money for a permanent series of Licklider lectures at MIT. So several ideas he had. One is that you shouldn't spend any more time in Washington than you had to. Nobody sensible likes that place. So he got the idea that you should only spend 2 years there. And then he got the idea that the only people who should fund the ARPA community should be people who came out of the ARPA community, and that person would spend 1 year as a deputy learning the job, and then 2 years as a director. So this is the stream of people who created the funding that funded most of the technology that we have today. How did Ivan get there? Well, he got drafted not long after he did Sketchpad, and Licklider did not want him to go to Vietnam. So they pulled some strings, and as a second lieutenant, he was made head of ARPA at the age of 26. That was one of the great moves of all time, because Ivan, even though each of these four guys were fantastic, you could argue that Ivan was the greatest of the four of them, because he was the youngest, he was the most vitally interested in the input-output human interface part of the thing. He was the person, for instance, who first funded Engelbart. A number of other things. Taylor, we'll meet him again a little bit later because he was one of the people who set up Xerox PARC, and Larry Roberts is best known for the ARPANET. Larry Roberts was Ivan Sutherland's roommate at Lincoln Labs. So here's Engelbart. A little bit later, I'm going to show in a couple of minutes. I'm going to show an Engelbart clip as I saw the system, which is not yet. This has happened before I came on the scene. Then then I was programming at just trying to see what it looks like here. I was programming at Air Training Command in the Air Force in the early 60s. And some unknown programmer came up with a great idea, because back then they didn't really have operating systems, or most places would build their own little operating system to help them process batch jobs and something. And Air Training Command had many different bases. A lot of them had Burroughs 220s, and somebody came up with this great idea for how to make data sensible to people. And that is the following. Each record on one of the 220's tapes was a long thing. Tapes didn't move very fast back then. Could write long records on them. And they were in 3 parts. The first part were a set of pointers back into the second part, which were a set of procedures that knew about the third part, which were the set of data records. Okay, and so the way you use these things, so the operating system was minimal, right? All you had to do was to read this thing into the core memory of the Burroughs 220 and start jumping indirect, in fact doing indirect procedure calls indirectly through these guys. These guys were in a standard order that had to do with reading and writing and finding out how many fields the data had. These procedures knew how to give the answers that these and the behaviors that these guys did. And the whole mess here knew what to do with these things down there, which are never touched directly by anybody. Is that a great idea? Don't you wish you had that on the internet? I thought it was a pretty good idea. Never been able to find out who had this idea. It was there when I arrived in 1961. Somebody had just done it. And it worked extremely well until the government decided everybody had to program in COBOL a few years later, and then it got thrown out. So this is my first, I believe this antedates all other forms of abstract data types that I know about. There's an early paper by Doug Ross that has some of these ideas from MIT. But I think this was an original invention by somebody. And it stuck in my mind. The other thing that I learned there, which I'm not going to try and explain, is it just happened that the third machine I ever learned was the Burroughs B5000, which is probably the greatest, not probably, it was the greatest machine architecture ever designed. I think 7 out of the 10 best software ideas ever thought up are in the hardware of this machine. And I will not try and explain what all of them are, but it was basically a crashless machine. It was the first machine to do what is known as capability addressing built into the hardware. One of the first machines to have a stack. The first machine to have byte codes. There are no addresses allowed in the code. All the code is relocatable. And in fact, it was kind of an object-oriented machine, although this is before people knew how to handle it that way. It was actually done for Algol 57, Algol 58, which on this machine was called Balgol back then. But by the time they got around to building the machine, Barton, the guy who designed the B5000, had designed the first modern, what I consider the first modern compiler, which ran on the Burroughs 220. And Knuth was one of the programmers of it. And why do I say modern? I think everybody in here knows what I mean when I say pass and a half compiler, which is a compiler that streams once through the source code, puts in fix-up pointers as it goes, and then as it finds out information about for references, fixes them up. The first one of those ran on the Burroughs 220. When Barton was designing it, he realized that the intermediate output of the compiler was actually more interesting than the Burroughs 220 machine code. So he thought about, why not just design a machine to run the direct output of the compiler and forget about all this bullshit down below, which had nothing to do with higher level languages. I commend his paper to you. I think one of the greatest papers ever written in computer science, called A New Approach to the Functional Design of a Digital Computer. Western Joint Computer Conference, 1961. It's only 4 pages long, and it gives the complete architecture of this system. I should mention, by the way, Java is a hot thing now. The virtual machine on the B5000 is much better than Java's. And in fact, all of the virtual machines that we did at Xerox PARC were based on this particular architecture. Anybody who wants to do a good virtual machine should avail themselves of that information rather than just trying to roll their own. Here's another thing that I came across in 1965, which is Gordon Moore's original graph saying what was going to happen to silicon, published in Datamation 1965. I read it while I was helping debug this infamous system called the Chippewa operating system for the 6600 in Seymour Cray's lab. It was back when he still worked for Control Data. So this is on semi-log paper. And first thing Moore did was just plot what was happening with integrated circuits from 1959 up to 65, and noticed that it was an exponential power of 2 every year, and started asking questions about what would it be like if you could continue that. Then a few years later, he did a more careful analysis and said, well, it's not going to be worse than a factor of 2 every 2 years. That's this red line. And here's the line for memory, dynamic RAM memory, as it started in about 1971. So Gordon Moore, on the basis of physical principles, and because he picked the right kind of silicon, MOS silicon, to look at, this is what led many people astray, because back in those days it was so slow that nobody would ever think of building a computer about it, because it works like blowing up a balloon with, it's like basically a capacitive-based way of doing switching, and so you have to put a lot of charge into an MOS transistor in order to get it to switch. It took a long time. But Gordon Moore looked at it in part, so I talked with him about it once, in part just because it was so much simpler to make than bipolar that he could actually do some math on it. Bipolar had like 14 layers and it was very complicated. But the MOS, he realized that the smaller you make an MOS transistor, the faster it is going to be able to switch. And so his main question was, how small can we make these guys and still have them be a transistor? And the answer back then was about 5,000 electrons, which we're now getting close to. So 5,000 electrons took his graph out to about 1995. So this is one of the great 30-year predictions of all time. And of course, everybody here knows that he did the other thing you need to do to predict the future, which is he helped invent it, right? So he left Fairchild and was one of the founders of Intel and is worth a few billion. It's not worth as much as Bill Gates, but a few billion is nothing to sneeze at. Okay. So I have to tell you that when I first saw this, it meant nothing to me, because I was debugging a machine that ran at 10 MIPS in 1965, and it required liquid Freon cooling. There was no particular way of extrapolating at that time. I found myself at Utah, and at Utah, the first thing, when you walk into Dave Evans' office, this is what he looked like. He's a real friendly guy. But before he even got a desk, he had a pile of these things on it, about this high. So the first thing he would do is give it to you and say, take this and read it. So that, and then you're supposed to come back, and if you could talk sensibly about it, then he would give you a desk. And it happened on my desk was a pile of tapes and listings that was supposed to be the Algol compiler for the UNIVAC 1108 that the University of Utah had. But in fact, it turned out to be the first Simula system. And here's another guy I ran into. Now, I've made this really murky. This, in fact, is not even a picture of Bob Barton, because I think we have determined that cameras cannot take pictures of him. He was called the Ghost Who Walks because he was often seen in Merrill Engineering Building, but he was never seen entering or leaving it. And in fact, he kind of hated the whole idea of school, and he kind of hated graduate students and really hated Burroughs. And, but Dave Evans had convinced him to leave Burroughs for a year and be a professor of sorts at the University of Utah. I'll just tell you one Barton story, which is I took this course called Advanced Systems Design, and he handed out this sheet in the first day, and he said, well, there's something known about, this is in 1966, there's something known about advanced system design, and it's all written down here, and I expect you all to learn this and understand it. He said, but my job this year is to firmly disabuse you of any fondly held notions you might have brought into this classroom. He spent the entire classroom simply garbage collecting our brains. It's one of the greatest educational experiences I've ever had. He never referred to advanced systems programming again, but he expected that we would read all of these things. What he was concerned was that none of us could think. And there were many dimensions to his complaints about how we weren't able to think. And during this year, he explored each and every one of them. The result of this, and of course he hated pretty much everything that had been done all up to then in the 60s, particularly by IBM. And pretty much anything that we thought might be a good idea, he had 55 reasons why it was a terrible idea. Now, you think, gee whiz, this is kind of a downer taking a course from... But you have to realize this guy had the eloquence of William F. Buckley, although he was to the left in his political leanings. He was one of the most fascinating people you can ever imagine running into, and he was extremely well-read. His degree was in mathematics, and he was extremely well-read in philosophy, and it was a wonderful experience. Now, the result of that class was that the students who were left at the end of it were free. And what I mean by free is he had completely removed all traces of religion about every phase of computer science. That meant there was nothing that we could not, there was no thought that we could not have. This is the best thing a professor can ever do. Instead of putting knowledge into our mind, he removed it. It was the most valuable experience I had in graduate school because, and he wouldn't talk about the B5000. I had to resort to odd strategies like asking his wife what it was like when he invented. It turned out he invented the whole thing over one weekend. Had all of the ideas. He woke up in the middle of the night with all of the ideas for this machine and just came down. It actually frightened him. We found out he could drink beer. And the problem was he was about 6'4", huge guy, and he could drink any of us. He could drink Australians under the table. So it was we actually approached him in relays. One of us would go and drink. So it'd take about 4 graduate students in a row to get him to drink enough beer, because Utah was a 3-2 beer state. You know, so but eventually you could get him taught. So this is one of the great geniuses that has lived in our field. Completely unappreciated even today. If you look at what he did in 1961 and 1962, and you look at what Intel and Motorola sells today, I mean, it just is pathetic. It turns your stomach. Turns mine anyway. Well, there's this pile of stuff on my desk that turned out not to be algol at all. It was Simula. It was an algol that had been doctored to make a Simula. And in the process of finding out what it was, we realized it was a programming language that did the same kinds of things with sequential code as Sketchpad did. The data structures were basically very similar. And this had the disadvantage that it wasn't as beautiful as the constraint-solving methods of Sketchpad, but on the other hand, you could do many more things with it because you weren't limited to what a constraint solver could do. This is a huge revelation. Now here's one of these opportunities when you wind up with something new. So data structures and procedures were the way to program. And if you held on to your pink thoughts and looked at Simula, as most people did, you would wind up inventing abstract data types, which many people did. Happened in the 70s. Now this is a really weak thing, because an abstract data type is kind of a slow way of doing what data structures do. And why do I say that? Because an abstract data type still thinks that you're supposed to use a generalized assignment statement on its simulated fields. Okay, and assignment statement programming is not a very strong way of doing things, and so most of the abstract data type languages have wound up requiring about the same amount of code to program things as data structure languages before them. They didn't show this factor of 10 difference that we found from OOP. Now there's a different way of looking at this, and it came about because one of my undergraduate degrees was in molecular biology, and I had read this book a few years before, published in '65, called The Molecular Biology of the Gene, and in it had an assay for the first time ever of a bacterium, E. coli bacterium, such as we have millions of in our stomach, And this assay is kind of interesting. It's about 70% water, but it has about 120 million organic components. That is, things that interact with each other informationally. And if you were to represent just those, forgetting about the water, it's about 100 gigabytes as a parallel information processing system. And when I made this slide, it was 200,000, well, how about 50,000 2-megabyte desktops in one of these Ecolis, and it was fast. If you take an atom as being the size of a size of a tennis ball, then one of these white proteins here has about 5,000 atoms, so it's about the size of a Volkswagen. And these guys can move their own length in about 2 nanoseconds. Now, if you scale that up, that's faster than the speed of light. Right? Anybody ever wonder why chemistry works? This is, it's really amazing to me that they never tell you in high school. So it's actually the smarter kids that wind up rejecting chemistry. Because how can the molecules find each other? It just really doesn't make sense if you actually think about it. The only way it makes sense is to realize just how much thermal agitation there is as you go down there. For instance, the deceleration on a bacterium in water is about 1 million Gs. Water is like asphalt to these things. They are incredibly strong. When they stop lashing their tail, they stop. There's no inertia of any kind here. And the thermal agitation, as I say, is such if it were scaled up, it would be things moving 8 or 10 feet in a couple of nanoseconds. So if you can imagine what that is like, you can imagine why biochemistry actually works. So that's a pretty complicated thing. And furthermore, it's only 1/500th the size of the cells in our body, and we have between 10 and 100 trillion of them. So when you start thinking, these cells have 60 billion organic components as opposed to 120 million. And yet, 50 cell divisions will make an entire baby. Now, if you compare this against computing even today, even against the internet, with all the computers on it, but especially if you think about it compared to what computing was like back in the 60s, you'll see that this constitutes a different class of organizing complex dynamic structures. They just aren't like computing machinery at all. And this is what I got from Simula. So I thought of Simula as not a better old thing, but almost a new thing, and got this hit that one of the great ideas you could ever have in doing programming was to organize it the way biological cells are organized. And that has progressed along. So you have this nice idea of encapsulation, which is the main strength of it. You have an even more weird thing that's partially from Simula, that you can simulate anything, including data structures if you want to go back to them. But in fact, you get to deal with many, many more things in a much more natural way using an architecture that we know from biology scales incredibly. And you have something that biology doesn't do, which is the DNA is not in the cells here, but it's extracted out. And so there's only one copy of the DNA, which if you twitch it, everybody is going to feel that. So that was a huge, that was the last, that happened to me in November '66. That was the last time I ever thought about doing procedural and data structure programming. I just realized that that was just an artifact of the past. It meant nothing. It had nothing to do with the destiny of computers in any way. So then I saw, let's see if this works now. If this thing has gotten. Then Engelbart came to Utah. And in those days, he traveled with a projector. You could stop and start because people weren't used to seeing cursors. So he'd stop the thing.
So I can say, I'd like to go to produce, but I'd like to go to produce. They get big. I'd like to say one branch only, and let me look just that low, and I see it. Oh, I can say, I'd like to see one line only. I can see it. But there's another thing I can do. There's a root dice that I have here. So here, I'm afraid I'll need a different picture than you. So here's what I drew with a picture drawing capability here. It's a slight map if I start from work, and here's the route I seem to have to go to pick up all the materials. And that's my plan for getting home tonight. But if I want to, I can say, the library, what am I supposed to pick up there? I can just point to that, and oh, I see, overdue books and all. Well, there was a statement there with that name on it. Go back. What am I supposed to pick up at the drugstore? I see, you're interesting. All right. Market can do things if I want to. Just say, I'd like to interchange produce and canned materials. Bingo. And they're all numbered rightly if I care to look. Interchanging them very quickly. Cans are going to get interchanged with produce. They do it and all gets renumbered.
So it's pretty sickening to realize that this was done on a 192K machine that was time-shared. Did you notice the response? Ever wish your PC or Macintosh would have that response? Well, you can't. They're too fast. Because they're too fast, nobody bothers to program them in a way that humans can use them. But the Engelbart people really understood that this was all about close interaction, and so they really paid attention to a lot of these things. This is a beautiful system in so many ways. And I don't know that Engelbart has been here to talk, but he really deserves to say more about all. They did conferencing. They had programmers up in Oregon that worked with the programmers down in Menlo Park. Things that people are still trying to do today, he did very successfully in the late 60s. Well, that made a huge impression on me. And so around that time, I got involved with an engineer who wanted to do a little machine, and together we did this thing called the Flex machine. This is a picture of it on its own display. The first object-oriented language I designed ran on this machine directly in the hardware. So I made many mistakes on this machine. One of them was just trying to scale the B5000 down into it directly. We learned from that experience that, as Barton used to say, good ideas don't often scale. It had one of the earliest clipping, dividing window system and multiple windows and a whole bunch of things. So windows were actually a pretty current idea back then. So another thing I saw early on was this system at Rand Corporation. At the same time whoop, I didn't mean that. Go back. So Rand had invented the tablet the same year the mouse was invented, 1964. They built this system. Whoops.
First we erase a flow arrow, then move the connector out of the way so that we may draw a box in its place.
Sees he wants a box and makes one for him. Now it's recognizing his printing.
The printing in the box is being used as commentary only in this case. The box is slightly too large, so we may change its size.
That's where modern-day window control came from, literally.
Then draw a flow from the connector to the box. Attach a decision element to the box and draw a flow from it to scan. We then erase the flow arrows attached to the process post new area and move the box to a new position. This allows us to draw a new box.
Okay. Nice, huh? So one of these days, I have the whole movie, and Dave remembers well, I used to show it to the group every few months at Xerox PARC, because what we wanted was something that nice. I showed that movie at Apple when they were doing the Newton and said, you know, people have already done a really great hand character recognizer. Why don't you use it? No, we're going to recognize handwriting. I said, well, you can't recognize handwriting because people can't even recognize their own handwriting half the time. They said, well, Go Corporation is doing it. I said, they can't be doing it. It's not possible. Why don't you do this? This is a great recognizer done by Gabe Groner. It's written up in 1966, and this system was around 1968, or I was 68 when I saw it. Too bad I can't talk about it more because it was beautiful. First modalist system. truly beautiful in every way. And right around that summer, I had seen a little square inch of glass with a few blinking lights on it, little neon lights. It was the first flat panel display at the University of Illinois. And then in the fall, I visited Seymour Papert for the first time and got an enormous, enormous life-changing insight. And the insight was that the computer is not a tool. The computer is not a vehicle. That's the way we were thinking about it. Engelbart was sort of thinking about it as a Model T compared to IBM's railroads. And it's not a bad metaphor, personal computing. But what Seymour was doing with children had no interesting analogy to things like tools or to vehicles. The only analogy it had that could work at all was an analogy to the printing press. Because what it was a vehicle for representing powerful ideas, the powerful ideas of our civilization in a concrete form that children could actually learn, not in an abstract form, or the abstract form was actually a concrete way of dealing with these things. And I'll never forget that day, on the plane coming back from MIT, I designed this machine and made a cardboard model of it when I got back, and it later became called the Dynabook, because a kid's computer can't work on a desk. Kids are mobile. Kids have to go places, and there are many things we did. This was hollow, so you could fill it up with lead pellets and see how heavy it would get before anybody didn't want to carry it anymore. It turns out, back in those days, before people had to buy these things because they worked for companies, the limit was about 2 pounds, about 1 kilogram. Beyond that, it was too heavy. I think that's still a good figure today. 2 pounds. And the other thing we discovered, of all the different ways of making one of these things, the main thing you wanted to do was to have it be really slim in at least one dimension. And the reason was you always have to carry other things too. So portability became defined as meaning you could carry other things too. We realized that this was a different kind of thing than the desktop computer. We thought about how good would you have to make it to do mundane things on it, like we do on paper. Paper, you can write the Declaration of Independence on it, but you also put grocery lists on. So one of the imagined things we actually did was to carry this in to a supermarket in Salt Lake City and imagine what it would be like to have your grocery list on this thing, and you have to walk out with 2 bags of groceries, plus this thing. So those are the kinds of thoughts in the late 60s about this machine, which was called the kiddie computer back then. And because I had a philosophical turn of mind as well, thinking about this stuff while I was trying to write my thesis, I realized that time-sharing systems, desktop computers, and whatever this thing was actually constituted 3 different kinds of information systems, and it reminded me of something I'd seen before, which is in the history of the book. So these manuscripts cost about $2 million. Typical library would be about 4 times the size of this room, and each book would have its own desk. The books were chained to the desk. They'd often have precious jewels on them because the jewels were nothing compared to the cost of one of these books. It often took as long as 10 to 15 years to make one of these books. To give you an example, there were only 371 books in the Vatican Library in the year 1400. It's one of the largest libraries in Europe. The richest man in France, who was the brother of the king, Jean-Duc de Berry, had 154 books when he died, and he was a bibliophile. He had these books made for him. And one of the best $25 you can ever spend is to get a facsimile of one of the books he had made for himself, which is called the Book of Hours of Jean-Duc de Berry. It's marvelous, and it gives you a bit of a sense of what these books were like, and also what is lost by simply trying to photograph them. They're renderings and capturings of the charisma of an basically oral society. And the Gutenberg Bibles were intended to look like these guys. And that was sort of the connection I made was, oh yeah, Nobody knows what a computer should look like. So the best we could think of for personal computing back then is to make it look like a time-sharing terminal without the central mainframe. And it's just what a Gutenberg Bible is. It's the same size. Gutenberg had 253 characters in his font just so he could imitate every ligature and abbreviation that the medieval scribes used. They had people come in and illuminate these books. And at the Nuremberg Book Fair in 1454, 20 of these books were shown for the first time. And they marveled, of course, at how alike these books were. That was a new idea. In fact, the errors in them were the same. And a place that was right was going to be right in all of the books. That was a displacing kind of idea. And they were cheap. Not cheap by our standards, but compared to these things, they were only 3 years of a clerk's wages. That's about $60,000. So this is a kind of a workstation. And if you think about that, it fit well into what these machines, for instance, the LINC, the handmade LINC was about a $20,000 machine. And then about 50 years later came the great hero in printing, was a guy by the name of Aldus, whose last name was not PageMaker. That's where the company got their idea. His last name was Minucius, or if you like colloquialisms, which most people hate, his real name was Aldo Minutio. He's thought of as Aldus today. And he made books that are the size books that we use today. Books that are like this size or a little bit bigger, and he made them that size because he went out in the streets of Venice and measured people's saddlebags. Because the first offering from his press was called the Portable Library. And what he printed was not Bibles, but everything the Greeks and the Romans ever wrote. He and his sons went all over Europe gathering up everything that had ever been written. And they published 40,000 different titles in the 30 years that his press existed. 40,000 different titles. Each press run was about 5,000 books or so. Now, even though I'm running out of time, it's worthwhile just pausing on one thing to ask the group here if anybody knows what the actual invention of printing was. Anybody know? What was no, movable type was invented by the Chinese in the 1st or 2nd century AD. Yes? Pardon?
Bag-bound paper.
No. Chinese invented paper too. Yes, Paul?
Standard dies.
Yes. Okay, here's the way it worked. The Chinese invented all this stuff centuries before, thousands of years before. They had the whole rigmarole. They knew how they had presses that would press these things together. They had movable type and everything. The problem was that it took forever to get a font up. And it wasn't just because of the Chinese characters that you needed 4,000 of them. Think about how many little things you need to print a book. So the secret here is that Gutenberg was a goldsmith, and if you've ever worked gold, it's a soft metal. You can work it with other metals. And so Gutenberg went through the following thought process at some point when he realized that he could make a steel die that was the character as he wanted that character. That steel die was tough enough to just strike negative impressions of itself in copper or brass. That copper or brass could then be poured with metals softer than it, like lead. And so a standard type maker in those days could make between 2,000 and 4,000 pieces of type a day. This is why the printing press spread. And you should think about the connection of this to Moore's law. Right? The printing press never would have happened the way it did if it hadn't been for the proliferation of what served as the bits. You had to be able to have these bits spread out exponentially so that anybody could make these things fairly easily and in great quantity. Well, that led to a bunch of different thoughts because the belief system for each one of these areas is completely different. And in fact, in history, what happened between here and here didn't really count. That happens to be where we are in computing today. Nothing that is happening between personal computing and this next phase really counts. It's all about this stuff. Almost everybody today, 100 million personal computers in the world, almost everybody today is not using hyperlinks. Almost everybody today is not simulating. Those are the two things that computers are about. But what almost everybody today are doing is simulating the older culture, the paper culture. And this is a recapitulation of what happened back then. So there are many interesting things. So one way of transforming this into a way of thinking is to think of each one of these as a belief system. And I call them the institutional belief system, the personal belief system, and the intimate belief system. And you can play games writing different properties of these. Just the main ones we were thinking about back then, where this one is going to be driven by the integrated circuit, and this one would be driven by wireless. Many people do not realize it, but I hope you get Larry Roberts here sometime to realize that his plan for doing the ARPANET was not just to wind up with something like the internet, but to do most of it wireless back in the late 60s. And in fact, when I first came here to the Bay Area, one of the first things I did was to ride around in an old Ford van that Stanford Research Institute had, SRI had, that had a Model 33 teletype in the back of the thing, and this very, very expensive transponder that would get 300 baud, but it would do it with wireless. You could drive anywhere and be logged into Engelbart's SDS 940. And Larry Roberts had a very elaborate plan that he tried to implement before ARPA got shut down to give everybody a handheld terminal and do everything via the power of the network. And if you think about that as a model for third world countries, especially who can't afford desktop machines, it's a really good one. He wrote many papers about this, and it's a very interesting side story here. Well, I have to be careful with this one because this has been improved over the years. We've gone back to this many, many times. Larry Tesler did a really great version of this at Apple a few years ago. Everybody has their own version. Most important idea is just thinking of these as being really different and trying to understand what is different about them. The other thing that was going on around 1969 was Ivan Sutherland had come to Utah, where I still was, and he brought with him the first virtual reality helmet. Here's an example of somebody grabbing. You could grab things and move them around. And we realized that it wasn't going to be too long before this would be an alternative way of thinking about a Dynabook. And in fact, it makes a lot of sense when you're riding on an airplane to be able to have a virtual display rather than a real physical one. Another person I met back then, I have two slides. This is one of his favorite comments, life is complex. But for this occasion, the actual should have been, I have a plane to catch. He was out visiting Utah, and there's this long, I think it had something to do with the, I was on several ARPANET committees, so I think it was an ARPANET committee thing he was at. He had to give a talk, and it dragged on, and finally he had prepared this hour talk, and he only had 15 minutes before he had to go to the plane. So he gave the entire talk in 15 minutes, and it was just the best talk I've ever heard in my life. You know, it was done at maybe 1.1 or 1.2 Lamsons, a little faster than he usually talks. And it could not have been clearer. And it was all about capability operating systems. And one of the things I gleaned from this, and this is my diagram, not Butler's, but it wasn't really an object-oriented system, but a capability system is darn close to an object system. So if you're thinking about different kinds of servers, that each object is a kind of a server, then one of the things you realize is that a lot of the services they're going to give have to be generic. And that was in this system. And that led to this realization that you have a kind of a matrix between generic behaviors that are basically your powerful ideas or your concepts, and then you have lots of different variations of types or object classes. And that made me realize that OOP could actually you could actually build an operating system out of OOP. In fact, you probably should, because you wouldn't have to have a lot of artificial distinctions that are in there, and these capability mechanisms would actually give you protection and limit access and so forth. The biggest problem with them was that the typical operating system process back then had an overhead of several K bytes to make one, and so you couldn't make little things like numbers out of this technique. So one of the things that stuck in my mind is we should find a way of making objects any size without incurring an overhead. Okay, another great book by Marvin Minsky. My other degree was in mathematics, so I happen to enjoy this, and this is the way I found out about Lisp, because Marvin showed how Gödel numbers work, and in order to illustrate it in here, he actually built a Lisp out of Gödel numbers, which is essentially what Gödel did, if you know that thing of, and it was an interesting idea. Oh yeah, you can use, sure, you can actually use integers to represent data structures, because you can factor them back out. And since Marvin and McCarthy had formed the AI project together and Marvin knew Lisp, he actually did a Lisp-like language in there. I said, oh, that's really interesting. Maybe I should look at Lisp. Because Lisp kind of looks horrible. And then I discovered this wonderful book, which I have about 20 copies of, discovered over the years that when I need an idea, I usually want it to come out this nice. So I go out and buy a fresh copy of this book. And when MIT Press quits printing it, I'll have to retire. They seem to use up their power. So I have to buy new ones periodically. So, however, let me commend this to you, because there's nothing more beautiful on this earth than the bottom of page 13. Okay, and there's nothing nicer than it only takes 13 pages to get to one of the great ideas of all time, which I think of as Maxwell. This is something like Maxwell's equations. This is like everything. This is everything. Now, of course, Turing machines are everything. But what's great about this is it's a Turing machine with slope. You don't have to write tons and tons of code to get it to do anything. It's a universal machine that's small and can grow up like this. And when I finally everybody here in this room remembers, who went through this thing, remembers the day they traced this thing with putting their fingers down. And at some point you realize, holy shit, this is everything. This is it. If you don't get that experience, you've missed one of the great things in computer science. Because to me, it divides the world up into two different classes of people. The people who think that you have to write endless amounts of grubby code to do anything, and the people who realize that what you should be spending most of your time on is the meta system, and let the meta system create the rest of the world for you. So that had a huge effect on me. I think what I'm going to do is skip the next tape in the instant. I have a very funny tape called LSD Kropotkin and the Magical Mystery Time-Sharing Machine, which was made at the AI project, which is where I went next, and we'll defer it to another time. It's basically a nice example of what people were doing. It shows one of the first modeless text editors done on the PDP-1 there, but I'll just pass on that. So I wanted to make one of these machines, and of course the flat screen display was a way off, so I thought, well, I'll get myself a Sony Tummy Chinatron, and I'll just wedge in there what a LINC has, and I'll get myself a modern version of the LINC for kids. So this is a thing called the Kitty Comp that I started designing. Then I wound up at Xerox PARC, and the chief scientist of Xerox wanted a research center, and they were smart enough to hire Bob Taylor to set it up. And Taylor knew every good PhD in the country because he had paid for their PhDs. And he started his siren song of gathering together a really fantastic group of people, which included Butler Lamson included a number of the people in this room. And that 5 years is the most fun I've had in a 5-year period. So I went from that kiddie comp to saying, okay, what we really need is something that looks like this. This is 1971. And this is called Minicom. And I said we need to make about 25 or 30 of these things so we can start working with children. We actually did, Dick Schaup and I did some of the display hardware for this machine, and then it got turned down by a guy who should have known better, who was known in the paper as Executive X. Meanwhile, other things were going on. We realized that because these kinds of machines weren't going to be very portable, that we'd need laser printing, and Gary Starkweather was there to do it. He was already working on a laser printer when I went to Xerox in 1971 and got it working late that year. And Butler Lamson had this meeting and said, you know, we've done so many bubblegum things in the 60s. What we should do at Xerox PARC is take an oath that we'll never do anything that isn't engineered for 100 users. So this was a novel thought. It was Butler's idea, and it was probably the greatest reason that PARC was a success, was not that it was so far out, but because it was actually incredibly conservative. And because of that, we actually wound up doing things that we'd already done in a half-assed way, in such a way that we could build 100 of them if they were personal computers, or run 100 users if it was a time-sharing system. It was a huge, huge thing, and it led to this idea, which today is called living labs. But the idea is you live in your own creations. Don't just do one and demo it. Make enough for everybody. If it's a programming language, it has to be documented and solid enough for 100 people to use it. So this became a pretty general principle for most everything that was done in the first 5 years of Xerox PARC. And the most amazing thing about it, astounding thing about it, was that with rare exceptions, it actually made things happen faster. Now, everybody knows why, right? Because that extra thought that you did when you were thinking, oh yeah, I have to engineer this for 100 users, prevented those bugs that add years onto the quick and dirty thing. So in fact, the stuff worked it was unbelievable. And I won't go through that, because a very interesting talk is about Xerox PARC in those days. I'm not going to do that, but it was a fascinating process. So around then, the idea is, oh, we have to do a Dynabook notebook kind of thing first, and then eventually we realized that the flat panel displays would actually be easier to make if they were small because of the contamination problems, and that there would be eventually something like this that you'd wear on your head. One of the reasons we didn't go much further with that is that the lightest head sensing device in those days weighed about 4.5 pounds. And then Nicholas Negroponte had been talking about simply wearing your computer. So to have something like a wristwatch that knew where your hand was in space, and when you walk from one room to another, it would know that you walked from one room to another. This today is called ubiquitous computing, and Nicholas has never gotten, as far as I can tell, a shred of credit. But in fact, this was his idea, and it was an early idea of his. So, oh yeah. So let me, do we have, yeah, tape 4 is what we want. Now, again, in the spirit of being historical, just by coincidence, I gave a talk in November '72. I think this is the right order to do this, I hope. November '72 to a conference which happened to be videotaped. Xerox PARC, that tape got lost. It was not in any of the holdings that we had. I saw an excerpt from that tape at a thing actually Paul Sappho and Ian Engelbart did in Japan. And I asked the Japanese, how did you get that? Oh, they said, we've had this for years. So I asked, well, can I have a copy of it, please? And so the only known copy of it, and how they got a hold of this damn thing I have no idea. But here's kind of the way I talked about this. Oops, sorry. Here's kind of the way I talked about this in 1972.
Okay, and perhaps lower. So let's sort of see what it is. You've already got that on. Could we have the lights down? And I'll grab the clicker if I don't. Okay, so you okay? Well, this is an existing device. It's a thing that Hewlett-Packard calls a pocket electronic slide rule. And it turns out that the way they decided to make it is so that it would fit into Bill Hewlett's shirt pocket. That was the way it was designed. It had to do everything that a slide rule would do, except to 10 places. And they actually spent almost an extra year on this thing to keep it to those size specifications. It has batteries, and it can indeed...
I'll just pause here for a second. I found out later that they actually retailored Hewlett's shirt a number of times. So this is a really, and the guy who can tell that story is Tom Osborne, who did the HP 35, if you remember that. I knew it was I got one of the very first ones because I knew Tom Osborne, and I had it for 2 weeks and had some wonderful experience with it, and then it got stolen. And that was when I realized that the new era had happened. You could actually steal a computer now.
be used on the grass. The power that it has and the size, portability and everything else make it something completely different. So different that Hewlett-Packard expects to sell 3 million of these in the next 5 years. People who would never buy a calculating machine of any kind buy these things for $400. Okay, so quantitative changes, if you make them large enough, are qualitative changes. Here's our conception of this gadget we call the Dynabook, also designed to be used in the grass. We don't have to worry about what's in it. It suffices to say that we designed the outside package first. So we want it to be no larger than a standard notebook. It's about 9 by 12. And we tried to make the specifications for it stylistic ones that had to do with the kind of quality that we wanted, with the idea that we would try to beat the whatever technologies needed to be beaten totally into submission in order to fulfill the insides of the gadget, and that in fact is what we're doing. So the idea here, the idea here is that it's supposed to be something like active paper. Okay? And it's not supposed to be worse than paper in any reasonable way. It's one of the problems with modern technologies. You always come up with something worse. We wanted to be able to handle things dynamically rather than statically the way paper did, but at no real loss in quality. So basically it has a display in which you can see things. You can think of it as being like a television display. Means for entering things. It has you can barely see it, a way for entering drawings, and it has a removable hunk of storage that will store one 500-page book, okay, or 1 million characters. Runs on batteries, and you can carry it with. It's portable by my definition of portability, okay, which is that you can carry something else too. Well, I'll tell you what you can do with it. In order to check out a few things, we decided to simulate it using current computer technology. So everything you're going to see from now on, and all the pictures in the paper are actual photographs taken at our lab. Okay, the simulation is in some sense, a real simulation. Okay, here's an example of the kind of display for text. Now, because this is an active medium, we can have any font that we want. In text files, for instance, we have almost all of this book typed in. We can look at this piece of text using any font that we wish. And fonts, of course, have a great quality.
Okay, so it goes on and on about why you should be able to read from it. So here's the old character generator, as it was known. And just for reference here is making a cap. This is a 20-point Lydian cursive font, and the page of text in the Lydian cursive back then looked like this. That actually compares quite favorably with anything today. We overdid practically everything. Like Gary Starkweather's first laser printer ever ran at a page a second at 500 pixels to the inch. It's a wonderful story. As he tells it, he needed to get some sort of laser printer from Xerox, and the only ones that they weren't selling back then happened to be the page a second one, and the Xerox 3600, and he tried to slow it down, but mechanically and inertia-wise, it was just set up to run at one speed, so he had to speed up the laser so he could actually, the first thing ever had a 24,000 RPM rotating mirror and laser. It was beautiful, this machine. It was beautiful. Okay, another thing we're thinking about, I'm going to have to go a little bit faster now. Another thing we're thinking about is psychological models. Again, I'm not going to go into this deeply because I've talked about it before. Piaget has a stage theory. You go through a kinesthetic stage. You have an iconic stage where the kid thinks there's more water in the tall glass, and later on, around the age of 13 or 14, you enter a symbolic phase where you can reason, or at least in Swiss French children of that age. So, there's no evidence that American teenagers ever achieve this stage. Still, perhaps the greatest single book ever written on this stuff, having nothing to do with computers but everything to do with the way people learn, is Jerome Brunner's Towards a Theory of Instruction. On October 13th, I'm going to be attending Jerome Brunner's 80th birthday party in New York City. This is just a great book, and he's a great writer. It has many wonderful things, and most of the deep insights we got about designing user interfaces came one way or another from this book. So his experiment was to take the kid who said there was more water in the tall glass and to put a shield, and discovered to his surprise that the kid changed his mind back. He said as soon as you prevented the kid from looking at this thing, the kid would say, oh no, there can't be more water. And what he would do is then take it away, and the kid says, no, there's more water. Put it in there, the kid says, no, there can't be more water. So if you have any 6-year-olds you want to torment. So one of Brunner's many conclusions was that the Piaget way of thinking about things did indeed have some stage dependence to it, but much more importantly that these mentalities are separate ways of thinking. It's not a metamorphosis like a caterpillar into a butterfly. It's multiple ways of knowing the world. They're operating at the same time, and the development of children tends to turn on the dominance in this order, but in fact by various tricks you can show that the other ones are there and you can make use of them. And that, if you think about it for user interface, is one of the most powerful ideas to think about, because the stage theory doesn't help you much. It kind of says you should wind up with MS-DOS if they're over 14. But in fact, if you look at Brunner's idea, it says, wow, you should try and get synergy between these different ways of knowing the world. People know the world simultaneously in more than one way, and they can remember and so forth in more than one way. So for instance, everybody here has had the experience of being able to remember a route better if they were the one driving the car rather than if they were a passenger. Everybody here has had the experience of clicking from one channel to another on cable TV into a movie they haven't seen for 20 years and being able to recognize that movie in just a couple of seconds, right? Okay, these are properties of these different mentalities, and they're quite incredible and can be exploited. So we were thinking about this stuff back then. Iconic thinking, Brunner's middle stage. So here's an easy one, that the area of the triangle is 1/2 the base times the height. But if you combine it with a little bit of logic, you can see that it's general for any triangle because you can divide things up. This is the power of Greek thought. Is the Greeks realized you could take things apart and put them back together again And you could, by simply dividing the triangle in half, you could get 2 cases, and therefore the rule had to be general. In fact, many of these, Dave Smith remembers all of these things that we used to look at. So the iconic ways of thinking about addition and multiplication, or a plus b times a plus b iconically is quite beautiful as well. Here's a different proof of Pythagoras' theorem, which is even nicer than the one that we used to think about back then, because it says here's the triangle, here's the c squared, and look, we can put 3 more triangles in there to make this larger thing, and it looks like there's just enough room for the a squared and the b squared plus the 4 triangles. Bingo. That's what iconic proofs are like, and they're wonderful. I noticed that one of the problems with the iconic proof is it doesn't tell you why this holds. It just shows you that it does. So it's actually an incredible, much more subtle thing to try and understand why right triangles have to have this property, besides just understanding that they do. Subtle difference between iconic and symbolic ways of thinking. So early on, we started thinking about we have to retreat from symbolic language down to the iconic, down to the kinesthetic, because there's a lot of good stuff down here. So our first essays at user interface design were saying, let's explore this down here, more right brain or more Brunner type mentality way of thinking. Here's a great book, Jacques Hadamard's Psychology of Invention in the Mathematical Field, that showed that most of the great mathematicians and physicists of the world did most of their thinking in terms of visualizations, and about 30% of them actually used kinesthetic sensations. Feynman wasn't included in this by an oversight, but he and Einstein were 2 of the most interesting ones that actually used their body in very strong ways for thinking about things. We looked at a programming language called Ambit G. This is a bubble sort done as kind of pattern matching diagrams against data structures. I didn't know Dave Smith was going to be here, but here's one he did, if Dave remembers it, of an iconic bubble sort. So the idea is, what he did here is to combine the 4 and the after into one diagram where the before links are the small ones and the after ones are the heavy ones, and there's a single comparison in here. So the idea is if this whole, remember this? No. So if this whole diagram is true, then you do what the fat links tell you to do. And we did actually quite a number of programs doing this stuff. I'm just going to skip this. There's a realization that there's more than one kind of programming language. And here's another metaphor that you can do beautiful things in each architecture, but the scale that you can work in depends a lot on what the actual premises of the architecture are. So the Greeks built beautiful buildings with posts and lintels, but you could not make them very big. Gothic cathedrals have very similar amount of material to the Parthenon. They're basically made out of air. But you can make them huge because you have this notion of the vaulted arch and the flying buttress. And of course, a geodesic dome, you can cover all the cathedrals made on this earth with the same amount of steel, because steel is more powerful under tension than it is under compression. Chuck Thacker. So this came about, remember I told you that our little Minicom thing got turned down by Executive X. And it turned out that Lamson and Thacker wanted to do it for me anyway. So they snuck over in September 72. And this is what Thacker said to me. He said, "Do you have any money?" And I said, "Well, yeah, I have about $230,000 that I was going to use to make a couple of these things out of these character generators." And they said, "Well, how would you like us to make your little machine for you?" And I said, "I'd like it." And I said, "What is it?" And he said, "Well, you want a kitty comp that works like a Dynabook. I want to build a 10 times faster Data General Nova 800. I want one that runs at 80 nanoseconds. And Butler wants a $500 PDP-10. So let's do a first shot at that. So we gave them all of the examples that we had done. And another thing that, here's Dan Ingalls. Another thing that happened is we had an argument in the hall about how powerful you could make programming languages. And I said, oh, half a page. Half a page, you can do the most powerful programming language in the world, because I knew about Lisp. And they said, put up or shut up. So, of course, I didn't show them Lisp. I sat down and spent a couple of weeks working out the actual first evaluator in itself for Smalltalk. And it came out to about a half a page. So the Smalltalk that we got was actually not anything like, Dave will remember, it was not anything like what we were planning on doing. It was just an accident. It just happened as a result of this bet. And everything would have been all right except Dan implemented it. In fact, when I got back from that trip where I showed the video, he had already had a version of the thing work, because of course he only had to take a half-page description, and he wrote about 700 lines of code on one of the mini computers there, and all of a sudden we had a working Smalltalk. And once you have a working language, you just really want to write code in it. And it kind of derailed things, although it was the language that Dave wrote his thesis in eventually, but it actually kind of derailed what the research was to just have this thing around. On the other hand, it's probably because we don't know whether the research would have been successful if Dan hadn't done this. So maybe I wouldn't be here talking to you if Dan hadn't decided to implement this thing, because Smalltalk might have been the most interesting thing that we wound up doing. We will never know. Meanwhile, Thacker had a bet. He bet a case of champagne with Bill Vidic, who was a Xerox executive, that you could do a real system in just 3 months. So he started the Alto on November 22nd, 1972, and around April Fool's Day in 1973, the Alto started working. One person, 2 technicians, and Ed McCrite did the disk drivers on the thing. So Thacker was a genius. He could just throw stuff at the wall and it would fall down machine. So the first picture ever shown on the Alto was this Cookie Monster, which we had done as part of our drawing experiments. And now I should show, let's see, let me just play the next tape here.
Effect.
Oops, it didn't get changed. Yep, change the next one, please. Just try and show you some of the things we were doing back then. So while he's changing the thing, sort of one of the summary things I could say here about this project is, the thing that was really great about this project was that we didn't have a huge plan, but we did have a huge vision. What I mean by vision is, like, how do you do a plan the best way? You write down all the things that should be, and then you erase them and try and smell the perfume that's left. Because if you write down all the things that should be and then try to do those things, you lose. Why? Because you haven't learned anything yet. This is why people who do things to plans usually don't do very interesting things. A much better way to do it is to do all the writing, but set the direction, and something much better will happen. And I think during these 5 years, just one thing after another that got done just turned out beautifully, because there wasn't any, we never had to justify the stuff. We weren't spending an enormous amount of money, but on the other hand, we didn't have to explain stuff we couldn't have explained. We couldn't exactly, because it was all aesthetic. There was so much, I mean, the part of the reason for doing a Smalltalk was just how beautiful it was to do something that was completely this way. Let's see what this, yeah. So here's the Alto Playroom. And this is the Alto synthesizing music. The Alto could do 12 voices in real time, like a Proteus, all by itself. Model 33 disk packs. Here's the Alto animation. Now think about that in reference to what you've seen on machines today. This is a system done by a child here, 15-year-old. The CAD system, I mean, the kid did. Okay, stop. Okay, change the tape, please. So we built a zillion altos. We connected them with Ethernet. We built 5 or 6 page-a-second laser printers and put them on as servers. We used the altos to construct a file system that's now today called client-server, although I think we should realize that client-server is actually a bad model. Peer-peer is what you really want. You want to have equally powered machines. The alto was so powerful, its inner engine back then was about a 6 MIP machine. You have to realize in 1972. So it was about a factor of 50 more than you got as somebody logging into a time-sharing system. That was made such an enormous difference. I weep today when I see people trying to develop code that's supposed to run in the future on today's machines. You have to do so much optimization. But we made it because the alto, we didn't have to optimize at all for the first few years. We just wrote the simplest code to try out the ideas, and we're able to iterate and iterate and iterate and iterate. How many people here know of Paul MacCready and the Gossamer Condor? Okay, here's an interesting story. MacCready never intended to win the Kramer Prize, but it happened his brother-in-law had gotten into $100,000 in debt, which MacCready decided to assume. So all of a sudden, MacCready was $100,000 in the hole. And he was driving through Arizona watching a hawk circling in the sky, and he suddenly realized that the current rate of exchange, the 40,000-pound Kramer Prize for man-powered flight was exactly $100,000. And so as he was driving along, he started thinking about, gee, I could pay off this debt if I could win this prize. Now, it happened that this prize, nobody had won this prize for 45 years. Many groups, large industrial groups, had tried over the years. MacCready won it within 6 months from that realization in the desert. How? Because he realized that the biggest problem, that the way everybody else had done it, is that they would build an aircraft, have a crash, and then spend another 6 or 8 months rebuilding the aircraft. These aircraft are incredibly elaborate. And he said, what we need is an aircraft that we can have 10 crashes a day. So he built one that you could actually fix with Scotch tape. It was just made out of Mylar and a couple of aluminum spars. And the thing started working within the first couple of weeks, and within 6 months he'd won the prize. And something we should all think about, that beyond a certain level, we simply cannot plan our systems. They are smarter than we are, but we have to negotiate with them. So whenever we build a system we can't negotiate with, and it gets beyond a certain size, we're dead. Here's a couple more things from back then. So here's the way we taught kids programming. We got them to make a couple of boxes. Each of them is an instance of class box. One's called Joe and one's called Jill, and they're both animating separately. And it gives the kids the idea that you can have multiple entities of the same type. Here's what the first Smalltalk class. Here's Marion Goldine. Now, one of the things that is kind of interest that people should, here's the first application she did, which was actually a painting program. You'll see she built this after I'd say about a month. She had seen some of our painting programs, so she decided she would do one of her own. So she picked up a square brush from the brush menu up there that she made. This whole thing, she has a different shape there. So this is the first known, that we know of, first known example of a tool being done by a child. What we would call an application today was done by this 12-year-old girl. And I should mention, for those of you who are interested in that, in the 70s, because there wasn't anything special about computing, the girls were just as interested in it as boys. So this is next year. She's teaching the class. She's now 13. And here's what one of her students did, which is something more like Mac Draw now. Instead of a painting system, it's actually an object-oriented illustration system. So there's a menu down here. The menu's saying grow, so she's going to make it grow smaller. Going to move the thing. So each one of these things has its own object identity, and each one of them is actually a class she made for doing polygons. So there's a selection handle that this 12-year-old girl, this is a girl by the name of Susan Hammett, did this. And now she's going to make it real small and give it a lot of sides, so she'll get a circle. Change the color. Now she's going to make a bunch of these to make a truck. So this is the color alto that Dick Schaup did around 1975. So here's more of. So the alto animation stuff was done by Steve Purcell, and it could animate about 120 square inches of graphics at 10 frames a second, which is very respectable even today. It was done much nicer. This machine had double buffering built into it, which is what you need if you know anything about animation. Trying to do it on today's machines without animation is kind of silly. Here's a system that some professional animators plus Ron Becker did. This is about 5 pages of Smalltalk. So the cell window is over there, the animation window is here, and what he's going to do is now give this ball that he just drew a path to follow. So it's following the path. Now he goes into the iconic menu here and picks up the step. So now he single steps it. What he wants to do is to get to the bottom, because the way, if you know anything about animation, the basic technique is called stretch and squash. So what he wants to do is to make a squashed form of the ball down here, and furthermore he wants to do it while the animation is running. Again, this is something that's quite disappointing about the animation systems today, is you have to do this stuff and then run it. But notice what he's doing. He has another transparent cell overlapped on that one. So he's not drawing on that picture. He's drawing a separate picture, but he's using it as a reference. And notice it's being inserted in there. And now he has to put in the specular reflection in order to get the animation effect to work. So this system was done over a single summer. It was about a 5-page
Here's
program.
another movie I made called Gallop.
So here's a 12-year-old girl, yet another one.
It's a horse galloping.
So she did a galloping horse in this
I can
animation.
write a program that has the horse galloping across the screen.
Then she added a feature to this adult program, which is to be able to take
Here's
any
the
two
horse again.
things and combine them into a single
And now I have
thing.
a jockey. I can superimpose the jockey on the horse to make a racehorse.
And then it becomes a single object to be animated.
Okay. Now I can have the jockey and the horse run across the screen by making another program.
Okay, so we're making progress here. So just a couple of other quick things. Here's a WYSIWYG retrieval system. You fill in the blanks, and it produces what the early Windows system looked like. Here's an early, slightly later version of the Windows system, I think around 1975. Multiple fonts. Here's an early version of the browser for debugging. This is probably around 1977 or 78. This is a Smalltalk 76 thing. This was designed by Larry Tesler. Here's an early desktop publishing system called the Galley Editor. And one of the things you might notice, this is what people are doing today. These are embedded objects, and when you put the mouse into one of them, it pops up a halo of its iconic menu. So each one of these things is a different, so this is a component-based system. You can put any kind of thing in there, and it's like OpenDoc. It's like OpenDoc. So that was a nice, really nice system. Oh, you know what happened? I need the other slide tray. I'm almost done. I appreciate your patience, because when I laid this thing out, I found it extremely difficult to tell a story that was somewhat like what happened, to give you a flavor of what it was like to do this stuff, and realizing that there's a limit to people's patience of listening to this stuff and looking at it. Maybe while he's changing, well, maybe he's already done it. Let's try. Oh, I know what he's having problems with. You know how these slide things work? You have to push down the thing to get to 0, or...
Your slides have sequence numbers?
Well, they once did. Yeah. So here's a multiple view system done by Trygve Reinskaug. So this is a planner. I think this is the first one ever done, really, that could show you. So this is a PERT chart at the top, I think a Gantt chart here, a sequence list here, and a list of things that you're interested in. This is done by a guy who was one of the designers of the Norwegian shipbuilding system. And so this is, I think, the first sophisticated multiple. And you see the problem with Windows, the way they're used today, is they're almost never used to give alternate views of things simultaneously. But that's the whole goddamn idea, is to be able to look at the same thing in different ways so you can understand it better. It was one of the really disappointing things in the commercialization of this stuff, that people were so paper-centric when they went at it. So the slogan for doing the user interface is, this is Brunner's progression: kinesthetic, iconic, symbolic. Doing with images make symbols, that everything is rooted in doing. And this general theory of user interface, which is kind of widely spread, says, well, you want to do things with your body in various ways, and having a kinesthetic feedback on the mouse would be even better. Icons, for the reason we were talking about, and you need to have some sort of scripting language underneath for a symbolic underpinning. And we realized that the retreat back to the iconic and the kinesthetic was only half the story, because the other half is that you want to go this direction as well. You want to recapitulate childhood. You want to learn by touching things, by seeing, but in fact you can't escape the need for abstract renderings of your ideas. It's very, very hard, for instance, to make the argument in Tom Paine's Common Sense using stained glass windows. Think about it. It just doesn't work. Television is no good for this either. So some very, very important arguments need symbolic renderings in order to actually work. And so here's the whole user interface idea. And so when the dust settled around 1974, 75, 76, we had this complete system, which of course Xerox turned down as a product idea. But that's a different story. It's not the story of the... And of course we had to take the Altos out to schools, and it turned out we had to steal the first 3 Altos out of Xerox PARC, because by the time it came time to take the Altos out into the schools, Xerox didn't want us to take the Altos out of the building anymore. So Steve Wire and I loaded several of them. The guard had never seen anybody steal a computer before, so instead of being underhanded about it, we simply put the things on trucks and took them out to a Dell station wagon and put them on there. It was very easy. Then we built this machine. This is 1978 now. This is called the NoteTaker. This machine has three 8086s in it, and a Smalltalk that now runs basically had 512K memory. And several people, Doug Fairbairn here who did it, Larry Tesler, and I think a couple of other, we built about 10 of these machines, had the experience of using them at least once in an airport. They weighed a fair amount. And, but these were the machines that we actually hoped that Xerox would put out. Machines that look kind of like an Osborne, don't they? Except they're about 5 years earlier. It was a very nice machine, actually. So I think this is a good place to end with a question about the Dynabook. Is there still a reason for the Dynabook now that we've had commercialization? Personal computing has been a howling success. Many people have made lots of money on it. Hundreds of millions of people are using it. And I would say, yeah, the worst thing we could possibly do is to continue the trend of just trying to stuff desktop computers into these things. We know these are going to get down to a couple of pounds very, very shortly. But the problem is they're never going to be a Dynabook unless their major reason for being is to help people to think better. Right? So having a printing press is not fulfilled if all you print is comic books, if all you print is pornography, if all you print is money. The printing press was fulfilled by printing things like this and things like this. This is my favorite meta program, the Constitution of the United States. Think about it. You can put it on a single sheet of paper. Here it's just a few tiny little papers, and it has been the controlling force for an organism made up of millions and millions of mutually conflicting parts and has not broken for more than 200 years. Nobody has ever built an organization that complex than this, and the only reason it works is because this is not a set of laws, but a set of principles. The only way we can get people to understand this is, I believe, is to have people understand the difference between laws, which our lawmakers obviously don't because they keep on making them. This is case-based reasoning of the worst traditional society way of doing things. See, why do I say that? Because King Solomon was the wisest man in the Bible, and it even says why. He knew more than 3,000 proverbs. The way proverbs work, if you come home from a trip and your spouse is glad to see you, then the reason is absence made the heart grow fonder. But if you come home from a trip and your spouse is not particularly glad to see you, then what is the reason? Out of sight, out of mind. So oral societies obviously do not list their proverbs because they're oral societies, and proverbs are basically stories that are evaluated the way stories are. You never worry about that the movie you see today contradicts the movie you saw last week. That's not what they're about. They're about how good they are now. So this is not a story. And this is not a story. Now the problem is unless we learn these other ways of thinking, the ways of logic and the ways of systems thinking, our natural biological tendencies are to grow up entirely in terms of a narrative. Television reinforces growing up in terms of a narrative. And this is probably the most disastrous thing that's happened because we are not only getting re-medievalized, we are actually, the world is now descending back to traditional society ways of thinking about things, which is, if a story is good, that's all I need to be convinced. Now, of course, we don't want to get rid of this because that would mean going to a theater and never being able to see the play. Right? You just see people, you'd never give yourself over to this thing. But think of the people who go to the exact same format as the theater called a political rally. Music, pageantry, fine words, and give themselves over to it. That can't be right. So these ways of thinking about the world are incredibly important to learn, and to learn when we're going to use one form of thinking or another. And I believe that Seymour Papert was right in the beginning, that the strongest ways of learning these new ways to think, these inventions of the Greeks and of the 17th century people and the 19th century people and the 20th century people, are to actually be able to build things using each of these ways of knowing the world. So from that standpoint, I think the world is more desperately in need of a Dynabook than ever. And one of the things that would be fun to see in the next few years is not to see the hardware of the Dynabook, because that was a lead pipe cinch from Moore's Law 30 years ago, but to actually see the software that a Dynabook actually needs. Thank you. Thank you. Thank you.